First time in the history. In 1893, a man proposed the correct structure for coordination compounds, and the man is Alfred Werner. Before him, hexamine cobalt 3 chloride was presented by the formula COCl3.6NH3. But the nature of the association indicated by dot was mysterious. Werner proposed the structure by CONH3 Cl3, where CO3 plus ions surrounded by 6 ammonia at the vertices of a octahedron. For his contribution, he was awarded Nobel Prize in Chemistry in 1913. He is known as the father of coordination chemistry. The postulates of Werner's theorem are: metal consists of two types of valences, primary and secondary. Primary is fulfilled by anions which are non-directional, and secondary is fulfilled by ligands which are directional. This theory explained the structure and isomerism of coordination compounds very well, but it is silent about the color of coordination compounds. If you ask question, why color? Then this theory gives you no answer. Same thing happens in case of magnetism of coordination compounds. It has no explanation behind the paramagnetism or diamagnetism. As a consequence, new theories are developed. And the new theories are effective atomic number rule, in short EN rule, valence bond theory, in short VBT, crystal field theory, in short CFT, adjusted or corrected crystal field theory or ligand field theory, in short LFT, and molecular orbital theory, in short MOT. In this lecture, we will concentrate only on valence bond theory, that is VBT. In the incoming classes, we will focus on the rest theories. Valence bond theory was first proposed by G.N. Lewis in 1916. Basically, it was not only explain the bonding in coordination compounds. In general, it was for the bonds shared by two electrons. He represented the molecules as Lewis structures. In 1927, the Hitler-London theory was formulated, which for the first time enabled the calculation for bonding properties of hydrogen molecules based on the quantum mechanical calculation. Hitler and London used Schrödinger wave equation to show how the wave functions of two hydrogen atoms join together to form a covalent bond. And then genius Linus Pauling came. He got Nobel Prize twice. In 1954, Nobel Prize in Chemistry, and in 1962, Nobel Peace Prize. He became one of the top 20 scientists of the 20th century. Pauling combined the fair electron ideas of Lewis with the Hitler-London theory to develop two new concepts in valence bond theory. First one is concept of resonance in 1928, and second one is concept of orbital hybridization in 1930. And that was the beginning of modern valence bond theory. Now take a glimpse of VBT. Hybridization. Intermixing of atomic orbitals is called hybridization. Prior to covalent bond formation, the valence atomic orbitals get hybridized. Each of the hybridized atomic orbitals contains one unpaired electron. Overlap. A covalent bond is formed between two atoms by the overlapping of their hybridized atomic orbitals.
we can clearly see 4 equivalent sp3 hybrid orbitals around each carbon atom. Each of these orbitals has one lobe bigger than the other and is occupied by a single unpaired electron. Now, consider a carbon atom having atomic number 6 in the ground state. Its electronic configuration is 1s2, 2s2, 2px1, 2py1, 2pz0. On excitation, an electron jumps from the 2s orbital to the 2pz orbital, resulting in an electronic configuration of 1s2, 2s1, 2px1, 2py1, 2pz1. In order to form 4 sigma bonds with other atoms, the 2s, 2px, 2py, and 2pz orbitals of this atom intermix. This process of intermixing of atomic orbitals is called hybridization. As a result, 4 equivalent orbitals called sp3 hybrid orbitals directed along the 4 corners of a regular tetrahedron are formed. When 2 such sp3 hybridized carbon atoms approach each other along the internuclear axis and overlap, a carbon-carbon sigma bond is formed. This bond has a bond length of 1.54 angstrom. 6 hydrogen atoms now approach and overlap the remaining 6 sp3 hybrid orbitals of both the carbon atoms, forming sigma bonds with bond length of 1.09 angstrom.
Now, come to valency bond theory for coordination compounds. You know, in coordination compounds, central metal atom or metal ion is surrounded by ligands. Here the electrons present in the metal ligand bonds are not equally contributed by the metal and ligands. During hybridization, metal center generates empty orbitals. Take the example of CO3 plus ion. You know, CO3 plus ion is 3d6 system. Its 4s, 4p and 4d subcells are completely vacant. During hybridization, partially filled 3d, 4s, 4p and 4d can take part in hybridization. Basically, number of orbital and nature of orbitals take part in hybridization depends on structure of the coordination compounds. In general, depending upon the geometry of complex, different n-1d, ns, np and nd orbitals take part in hybridization. You know, here n represents the outermost principal quantum number of neutral metal atom. These hybridized orbitals are completely directional in nature. If inner d subshells, that is n-1d subshell takes part in hybridization, then the complex is called inner orbital complex or low spin complex. And if the outer d subshell, that is nd subshell takes part in hybridization, then the complex is called outer orbital complex or high spin complex. In the case of CO3 plus ion, if this 3d subshell takes part in hybridization, then the complex will be inner orbital complex or low spin complex. And if these 4d subshells takes part in hybridization, then the complex is outer orbital complex or high spin complex. I think you understood why this is outer orbital complex and why this is inner orbital complex. Now the question is, why outer orbital complex is called high spin complex or why the inner orbital complex is called low spin complex? You know, the compounds which have unpaired electron or electrons show paramagnetism, and the spin-only magnetic moment is presented by the equation mu s is equal to root of n into n plus 2 Bohr magneton, where n is the number of unpaired electrons present in the complex. With increasing the number of unpaired electrons, mu s increases, and with decreasing the number of unpaired electrons, mu s decreases. Now, consider the outer orbital complex. Here the electrons present in the inner d subshells are unaffected by the hybridization because they do not take part in the hybridization. Hence, the number of unpaired electrons present in the metal ion remain unaltered after the complex formation. That is, the number of unpaired electrons present in the complex is maximum in the case of outer orbital complex formation. Hence, the outer orbital complex is called high spin complex. In the case of inner orbital complex, the inner d orbitals take part in the hybridization. So in case of CO3 plus ion, 3d takes part and 4d orbital has no role in the hybridization. Consider inner orbital octahedral complex. Then two vacant d orbitals are required for the hybridization, but there is no such vacant orbitals in 3d subshells. Then these two unpaired electrons gets paired up here and here. One comes here and another comes here, and the electronic rearrangements looks like this. These two vacant 3d orbitals take part in the hybridization along with 4s and 4p orbitals. But to do this, the number of unpaired electrons reduces. In this case, number of unpaired electron is 0. That is, the spin only magnetic moment is 0. Hence, the inner orbital complex is called low spin complex. Now, come to the second step of coordination bond formation. That is overlap of metal ligand orbitals. In this step, the ligands donate electrons to the empty hybrid orbitals of central metal atom or metal ion to form coordinate bond. In the case of octahedral hexaamine cobalt complex, first 6 hybridized orbitals get ready. Then 6 ammonia ligands approach to this hybridized orbital. Look here. Each ammonia contains a lone pair of electrons. The orbitals containing lone pair of electrons overlap with the empty hybridized orbital of the central metal atom in here CO3 plus ion, and finally formed hexaamine cobalt 3 complex. Since the hybridized orbitals are directional in nature, the 6 ammonia ligands positioned at the vertices of a octahedron. Now, look at the octahedral complexes in the light of valence bond theory. In octahedral complex, 6 ligands are placed in the vertices of a octahedron. Look here. 4 ligands are placed in the xy plane and other 2 are placed along z-axis. So for effective bonding, 6 hybridized orbitals are required and they must be oriented at the vertices of a octahedron. You know, s and p orbitals are oriented at the 4 vertices of a octahedron, and so they take part in hybridization. The remaining 2 orbitals comes from d subshell. It may be a inner d subshell or it may be a outer d subshell. Among the 5 d orbitals, all are not oriented properly to take part in hybridization to form octahedral complex. Only dz square and dx square minus y square orbitals are oriented at the vertices of a octahedron, and because of that they take part in hybridization. Overall, orbitals take part in hybridization are S, Px, Py, Pz, dz square and dx square minus y square. One point should be noted here. For an electronic configuration, dz square and dx square minus y square orbitals may come from inner d subshell or outer d subshell, or maybe from both subshell. Now consider case 1, where the outer orbital electronic configuration is in between d0 to d3. For example, take V2 plus ion, which is a d3 system. In this case, minimum 2 inner vacant d orbitals are always available for the hybridization. Look here. These 2 d orbitals are vacant. In the case of d0 system, there are 5 vacant inner d orbitals, and in case of d1 system, there are 4 vacant inner d orbitals, and so on. You know, outer d orbitals are more diffuse than the inner d orbitals. So, inner d orbitals always make strong bonds with the ligands compared to the outer d orbital ligand bonds. Hence, in the case of d0 to d3 system, inner d orbitals always take part in hybridization, and the hybridization is d2sp3. Here, d2 comes first because it comes from the inner d orbitals. So, we can say metals or metal ions having outer electronic configuration d0 to d3 always form inner orbital octahedral complexes. Now consider case 2, where the outer orbital electronic configuration of metal or metal ion is d4 to d6. For example, take CO3 plus ion, which is a 3d6 system. In this case, 2 vacant d orbitals may come from inner d subshell or outer d subshell. If the ligands are weak field ligands, then the outer d subshell take part in hybridization, not the inner d subshell. You see, to vacant these 2 inner d orbitals, you need to pair up these 2 electrons into these orbitals, and it requires energy. Weak field ligand forms weak bond with the metal or metal ions. Hence, the metal ligand bond energy is not sufficient to pair up these 2 electrons into this orbital. And because of that, fully vacant outer d orbitals take part in hybridization. In this case, the hybridization is sp3d2. Here, d2 comes last because it comes from outer d subshell. So we can say metals or metal ions having electronic configuration d4 to d6 form outer orbital complex or high spin complexes with the weak field ligands.
In hexafluorocobalt complex, cobalt free ion hybridizes Mt4s, 4p and 2 of the 4d orbitals to form 6sp 3d 2 orbitals, and 3 unhybridized 4d orbitals remain empty. In this complex, copper is in +3 oxidation state, and its 6sp 3d 2 hybrid orbitals point towards the corner of the octahedron. 2p orbitals of fluoride ions overlap with them to form 6 cobalt fluoride bonds. Each fluoride ion denotes a pair of electrons and forms cobalt fluoride bond. The compound is paramagnetic since it contains unpaired electrons. The compound is also called as outer orbital or high spin or spin-free complex, as it uses outer 4d orbital for hybridization.
Strong field ligands form strong bond with the metal or metal ions. In the case of strong field ligands, total metal ligand bond stability is sufficient to pair up the electrons into inner d subshell to produce 2 vacant inner d orbitals. So in presence of strong field ligands, these two electrons pair up in these orbitals easily, and electronic arrangements look like this. These two vacant inner d orbitals along with 4s and 4p take part in hybridization. Hence, the hybridization is d2sp3. So we can conclude that metals or metal ions having electronic configuration d4 to d6 form inner orbital or low spin complexes with the strong field ligands.
In cobalt 3 ion, there are 6 electrons in 3d orbital and 4s and 4p orbitals are empty. In hexamine cobalt complex, due to the presence of amino group which behaves as a strong ligand, electrons in 3d orbital of cobalt 3 ion get paired up. So cobalt 3 ion hybridizes Mt4s. 4p and 2 of 3d orbitals to form 6d2sp3 orbitals, and 3d orbitals remain unhybridized. In this complex, cobalt is in +3 oxidation state and its 6d2sp 3 hybrid orbitals point towards the corner of the octahedron. One of sp3 hybrid orbitals of nitrogen in amino group overlap with them to form 6 cobalt nitrogen bonds. Each amino group donates a pair of electrons and forms cobalt nitrogen bond. The compound is dimagnetic due to the absence of unpaired electrons.
Now observe an interesting thing. In case of electronic configuration d4 to d6, you have seen that it may form outer orbital complex or inner orbital complex. You know, spin only magnetic moment μs is equal to root of n into n plus 2 Bohr magneton. Outer orbital complexes of CO3 plus ion have 4 unpaired electrons. So, the spin only magnetic moment of this type of compound is root of 4 into 4 plus 2, that is root of 24 Bohr magneton. And inner orbital complexes of CO3 plus ion have no unpaired electrons. So the spin only magnetic moment is 0. You can experimentally measure the magnetic moment of a compound. So if you found a CO3 plus complex having magnetic moment near to root 24 Bohr magneton, then you can conclude that the complex is a outer orbital complex of CO3 plus and its hybridization is sp3d2. Again, if you found a CO3 plus complex having magnetic moment near to 0, then you can conclude that the complex is a inner orbital complex of CO3 plus and its hybridization is d2sp3. So, experimentally by measuring the magnetic moment of a compound, hybridization can be predicted. Now consider case 3, where the outer orbital electronic configuration of metal or metal ion is d7. Here is also the possibility of formation of outer orbital complex as well as inner orbital complex depending upon the nature of ligands. First consider weak field ligands. You know, weak field ligand metal bonds are weak. So these ligands are unable to pair up electrons or promote an electron from lower energy orbital to higher energy orbital. Hence, in this case, outer d orbitals take part in hybridization. That is, here the hybridization is sp3d2. So we can conclude that metals or metal ions having electronic configuration d7 form outer orbital complexes with the weak field ligands. Now consider d7 system in presence of strong field ligands. You know, strong field ligands form strong bonds with the metal or metal ion and it gives extra stability to the complex. Look at CO2 plus ion, which is a d7 system. In presence of strong field ligand, one electron from the 3d shaft shell promoted to 5s orbital like this, and another electron pair up here. The energy required for these two processes comes from the metal ligand bond stability. And then the electronic rearrangement of CO2 plus look like this. Here, two inner d orbitals are completely vacant. These two orbitals along with 4s and 4p orbitals take part in the hybridization. Hence, the hybridization is d2sp3. So, we can say that metals or metal ions having electronic configuration d7 form inner orbital complex or low spin complex in presence of strong field ligand. One point should be noted here. The promoted electron resides in 5s orbital. So, it is a very high energy electron. It has high tendency to escape from the complex. So, these types of complexes are very much prone to oxidation. For example, octahedral CO2 plus complex with strong field ligands easily release an electron to form CO3 plus octahedral complex. So, we can say that the inner orbital octahedral complexes of CO2 plus are very much prone to oxidation, or the inner orbital complexes of CO2 plus have high reducing power. Now consider case 4, where the electronic configuration of metal or metal ion is D8 to D10. Here the inner orbital complex formation is impossible. Suppose the case of Ni2 plus ion. This is a D8 system. To form inner orbital complex, you need to promote these two electrons into higher energy orbital. Promotion of two electrons from inner d shaft shell is unfavorable because it requires huge amount of energy. Metal ligand bond energy is not sufficient to supply this amount of energy. Hence, the inner orbital complex formation is not possible. The only possibility is outer orbital complex formation, which gives sp3d2 hybridization. So, the metals or metal ions having electronic configuration D8 to D9, D10 always form outer orbital octahedral complexes. Okay, now look at the square planar complexes in the light of valency bond theory. In square planar complex, 4 ligands are placed at the 4 corners of a square. Look here. All the ligands are placed in the xy plane and they are placed in the corners of a square. So, to form a square planar complex, 4 hybridized orbitals are required and their lobes must be at the corners of a square. You know, lobes of S, Px and Py orbitals are at the corners of a square. In fact, S orbital is spherically symmetrical orbital. So, other one orbital required for hybridization comes from d shaft shell. But the lobes of all d orbitals are not lying in the xy plane. Only the dx square minus y square orbital has the lobes in the xy plane. So, in the formation of square planar complex, the dx square minus y square orbital takes part in hybridization. Overall, the orbitals take part in hybridization are S, Px, Py and dx square minus y square. The orbital dx square minus y square may come from inner d shaft shell or outer d shaft shell. Now consider case 1, where the electronic configuration of metal ion is d0 to d4. In this case, always more than one inner d orbital remains vacant. You know, inner d orbital makes strong bond than the outer d orbital. So, this type of metal ion always forms inner orbital complex. In the case of Cr2 plus ion, this vacant inner d orbital takes part in hybridization. and the hybridization is dsp2. So we can conclude that metal ions having outer electronic configuration d0 to d4 always form inner orbital square planar complex. Now come to case 2, where the electronic configuration of metal ion is d5 to d8. Here, one vacant d orbital may come from inner d or outer d subshell. Take the example of Ni2 plus ion, where the electronic configuration is 3d8. Here, which d orbital takes part in hybridization basically depends on the nature of ligands. If the ligand belongs to weak field ligand, then outer d orbital takes part in hybridization. You know, weak field ligands form weak bonds. So, in this case, the metal ligand bond stability is not able to pair up two electrons in the inner 3d orbitals. As a result, weak field ligands form outer orbital or high spin complex, and the hybridization is sp2d. Now, take this situation in presence of strong field ligand. You know, strong field ligands makes strong bonds with the metal ion. Then the metal ligand bond stability is sufficient to pair up the electrons in the inner d orbital. In the case of Ni2 plus ion, these two electrons get paired up in presence of strong field ligand, and the electronic arrangement changes to this. Look here. Here, this inner d orbital is vacant and it takes part in hybridization along with 4s and 2 4p orbital. Hence, the hybridization is dsp2. So, we can conclude that strong field ligands form inner orbital or low spin complex.
In nickel 2 ion, there are 8 electrons in 3d orbital and 4s and 4p orbitals are empty. In tetracyanonickel complex, due to the presence of cyanide ion which behaves as a strong ligand, electrons in 3d orbital of nickel 2 ion get paired up. So nickel 2 ion hybridizes with empty 4s, 2 of 4p and 1 of 3d orbitals to form 4 dsp 2 orbitals, and 4 3d orbitals remain unhybridized. In this complex, nickel is in +2 oxidation state and its 4 dsp 2 hybrid orbitals point towards the corner of the square. One of the sp hybrid orbitals of carbon in cyanide ions overlap with them to form 4 nickel cyanide bonds. Each cyanide ion donates a pair of electrons and forms nickel cyanide bond. The compound is diamagnetic due to the absence of unpaired electrons.
Now, consider the magnetic moment of outer orbital and inner orbital complexes of Ni2 plus ion. You have seen that the number of unpaired electrons present in outer orbital complex of Ni2 plus ion is 2. So, its spin-only magnetic moment is √8 Bohr magneton. In the inner orbital complex of Ni2 plus ion, number of unpaired electron is 0. So, its spin-only magnetic moment is 0. Hence, by measuring the magnetic moment of a complex, hybridization can be predicted. Now consider case 3, where the electronic configuration of metal ion is d9 to d10. In this case, outer d orbital takes part in hybridization and the hybridization is sp2d. Take the example of Cu2 plus ion, which is a d9 system. In this case, inner orbital complex formation is then possible if the ligand bond stability is able to promote this electron into a higher energy orbit. But the total bond stability in square planar complex is less than that of octahedral complex, because in octahedral complex 6 metal ligand bond is present, whereas in square planar complex 4 metal ligand bond present. And for this, promotion of this electron into higher energy orbital is impossible. As a result, inner orbital complex formation is not favorable. So we can conclude that metal ions having electronic configuration D9 to D10 always form outer orbital square planar complex. Now look at the tetrahedral complexes in the light of valency bond theory. In tetrahedral complex, 4 ligands are placed at the vertices of a tetrahedron. So to form a tetrahedral complex, 4 hybridized orbitals are required, and their lobes must be at the vertices of a tetrahedron. The s and 3p orbitals take part in hybridization, and the hybridization in tetrahedral complex is sp3. So in the formation of tetrahedral complex, inner or outer d orbitals have no role. Hence, there is no concept of inner orbital or outer orbital tetrahedral complex. We are almost at the end of this lecture. Now concentrate on the merits of valency bond theory. It has all the merits which have Alfred Werner's theory. Additionally, it has some extra merits. Werner's theory was failed to explain the magnetic properties, but valency bond theory explains the magnetic properties of coordination compounds. It is able to give the answers of the question like why FeF6 4- is a paramagnetic substance and FeCN6 4- is a diamagnetic substance. In the both complexes, metal ion is Fe2+n, but the two complexes have different magnetic moments. This can be explained nicely with the help of valency bond theory. Fe2+ is a D6 system. The weak field ligand F- forms outer orbital complex with Fe2+. So there are 4 unpaired electrons present in the Fe F6 4- complex, and that's why this complex is a paramagnetic substance. But the strong field ligand Cn- forms inner orbital complex with Fe2+n, and because of that number of unpaired electron is 0. Hence, FeCN6 4- is a diamagnetic substance. But the magnetic moment also depends on the geometry of the complex. Valency bond theory is not able to predict the geometry of a complex. That is, which is the most favorable geometry for a given set of metal ion and ligand. If the geometry is known, then valency bond theory can explain the magnetic property. Otherwise, it is not able to predict the magnetic property. So, this is a demerit of valency bond theory. Along with this, there are many more demerits. For example, it is not able to explain the color of coordination compounds. Why a given metal ion forms different colored complexes with different ligands? Valency bond theory has no answer of this question. Next point is, it is not able to explain the stabilities of the complexes. And the most important point is, why some ligands are behaves as weak field ligand and some ligands are behaves as strong field ligand. Valency bond theory has no answer. You know, the property of a coordination compound very much depends on the nature of ligands. So, we will continue our hunting until we get the answers of these questions. But to do this, we have to remember the list of ligands according to their strength. That is, which ligands are weak field ligands, which ligands are borderline ligands, and which are strong field ligands. And this is the list of ligands. I think it is not so easy to remember all the ligands according to their strength. But we have to remember this list for the better understanding of coordination compounds. I have a trick which will help us to memorize this list, but this is in Bengali. The students who know Bengali, it will work for them. এইবার এসো সচিন, চলো আজ ফেলে নটোরিয়াস হাইড্রক্সাইড অক্সালেট। ওরে জল এনেছিস, নিচে ওটা পিয়ে নিস। অ্যামোনিয়ান বাইপিরিডিন, ফ্যানিও সাইনাইড কিং। ছড়ার প্রথম দুই লাইনে লুকিয়ে আছে উইকফিল্ড লিগ্যান্ড। এখানে এই স্ট্যান্ডস ফর আই মাইনাস, বার স্ট্যান্ডস ফর বিআর মাইনাস, এসো স্ট্যান্ডস ফর এস ডাবল মাইনাস, সচিন স্ট্যান্ডস ফর এসিএন মাইনাস, চলো স্ট্যান্ডস ফর সিএল মাইনাস, আজ স্ট্যান্ডস ফর অ্যাজাইড আয়ন, ফেলে স্ট্যান্ডস ফর ফ্লোরাইড আয়ন, নটো স্ট্যান্ডস ফর নাইট্রেট আয়ন, ইউরিয়াস স্ট্যান্ডস ফর ইউরিয়া এবং হাইড্রক্সাইড নিজেকেই তুলে ধরেছে। ছড়ার তৃতীয় ও চতুর্থ লাইনে বসে আছে বর্ডার লাইন লিগ্যান্ড, যারা কখনো উইকফিল্ড লিগ্যান্ডের মতো ব্যবহার করে, কখনো বা স্ট্রং ফিল্ড লিগ্যান্ডের মতো। এখানে অক্সালেট নিজেকে রিপ্রেজেন্ট করছে। ওরে স্ট্যান্ডস ফর ও ডাবল মাইনাস, জল নিজের কথা বলছে। এনেছিস স্ট্যান্ডস ফর এনসিএস মাইনাস। এখানে লক্ষ্য করার বিষয় হলো এসিএন মাইনাস এবং এনসিএস মাইনাস। ইলেকট্রন পেয়ার ডোনার অ্যাটম পরিবর্তনের সাথে সাথে লিগ্যান্ডের ফিল্ড স্ট্রেংথ পরিবর্তিত হচ্ছে। নিচে স্ট্যান্ডস ফর এনসি মাইনাস, ওটা স্ট্যান্ডস ফর EDTA4 মাইনাস, PA স্ট্যান্ডস ফর PY মানে পিরিডিন, নিশ স্ট্যান্ডস ফর NH3। ছড়ার পঞ্চম ও ষষ্ঠম লাইন দখল করে আছে বীর যোদ্ধা স্ট্রং ফিল্ড লিগ্যান্ড। এখানে অ্যামোনিয়া নিজের স্বরূপ বিকশিত করেছে। আন স্ট্যান্ডস ফর EN মানে ইথিলিন ডায়ামিন, বাইপিরিডিন নিজের ছটায় পরিস্ফুটিত। ফ্যান স্ট্যান্ডস ফর ফেন মানে অন 10 ফেনান্থ্রোলিন, নিউ স্ট্যান্ডস ফর নাইট্রাইট আয়ন, সাইনাইড নিজের ধ্বজা নিজেই উড়িয়েছে। শেষমেশ দ্য কিং অফ অল লিগ্যান্ডস, দ্য কিং কার্বন মনোক্সাইড।